Hi everyone, my name is Tejas Chopra and I am a senior software engineer at Netflix. My topic today is compacting small objects in cloud for high yield. The agenda for the talk is I'll give a brief introduction about myself. We'll discuss the problem statement, then get over some basics of what compaction is. We will discuss data structures such as blobs and blob tables, file system operations that had to be changed, and finally some results. I am a senior software engineer at Netflix. I work with the data storage platform team here at Netflix. My job is to architect solutions for Netflix studios and streaming platforms that generate exabytes of data and billions of assets. I'm also a keynote speaker and I talk on distributed systems, cloud, and blockchain. Prior to Netflix, I was a senior software engineer at Box, where again, I was architecting storage solutions to support millions of customers and petabytes of data. I have worked at companies such as Datrium, Samsung, Cadence, and Tensilica. A lot of enterprises today are moving to the cloud, and the cloud footprint is exponentially growing. When we think about cloud file systems, they provide a file system interface to objects that are stored in the object store in cloud. A simple approach is to map each file to an object in the object store. It has been observed that a lot of the cloud workloads contain many small files, and they are bursty in nature. Small-sized files are not really beneficial for cloud storage. And there are two reasons for this. One of them is request level costs. In order to perform cloud uploads, you actually pay for the puts, you pay for the storage, and finally you pay for the egress cost to read data out of the cloud. In fact, to upload a gigabyte file with 4 kilobyte puts is 57 times the cost of actually storing that file. The other reason is throttling. S3 best practices guideline says that if there are more than 300 puts or deletes or lists per second, or more than 800 gets per second for an object, S3 may actually rate limit. In fact, a 4 megabyte put is 1000 times faster than 1000 4 kilobyte puts. As you can see here, with an increase in object size, the average throughput also increases. There are several options when it comes to how files can be stored on the cloud. You could use databases, you could use Elastic File System, you could use S3. So EFS is the Elastic File System. It's a generic file system in the cloud. It actually charges only for storage, so there are no request level costs associated with it. The charges are $0.3 per gigabyte per month. DynamoDB is a database. It's a NoSQL database that has both request level costs and storage costs. It is 0.25 per gigabyte per month for one write per second and 0.09 per gigabyte per month for one read per second. S3, on the other hand, has 0.023 per gigabyte per month. So it is the lowest in terms of storage, but it has a cost of 0.005 cents per put. So what it boils down is to store 1 terabyte worth of 4 kilobyte files, assuming that there are 100 writes per second being performed by applications. With S3 as is, it'll take $1,366 per month. The interesting thing to note here is that the operation cost, that is the cost of puts, is 98% of the overall cost. It will take 5 years of storage to match this operation cost. With Elastic File System, the cost is $307, and because it does not charge per put, the operation cost is effectively 0%. In DynamoDB, it's $303, and the operation cost is 16%, which means it will take 5 days of storage in DynamoDB to match the operation cost. If we employ compaction with S3, then the cost comes down from $1,366 per month to $24 per month. And in fact, the operation cost is now just 0.001%, which means that it will only take 27 seconds of storage to match the operation cost. So what exactly is compaction? Compaction is a pluggable module on the client side. What it does is it packs the data into gigabyte-sized blobs and maintains an index of where the file is within the blob. So you can think of all these small files coming into a blob and you maintaining a footer that contains the location of these files within the blob. There is also a redundant client-side global index of all the files in all the blobs, as well as, like I said, an embedded index in every blob, which is really for fault tolerance. Uh, the data structure that I just talked about is a blob. A blob is a single immutable object on cloud. Data from multiple files that may or may not be related to each other is packed into a blob. And the footer of the blob contains information about the byte ranges of these files within the blob. So in effect, if you read all the footers of all the compacted blobs, you can recreate the world. We could have used SS tables, but it requires some form of sorting before persistence. The other data structure is a global blob table. It is actually an optimization over reading all the footers of all the blobs. It is a global table that contains information of all the files in all the blobs. And by nature, it is redundant because it can be recreated. Consistency is a challenge because blob creation happens on different clients that are getting these different files being uploaded to cloud and therefore is distributed in nature. In compaction, sufficient data needs to be accumulated before it gets compacted. Typically, the size that has worked well is around a gigabyte. Data is buffered on client nodes and it is not durable until it is pushed to cloud. Because the client machines are ephemeral in nature and they can go down anytime, this data is not considered durable. The compaction policy is actually specified at mount time, and there are different ways in which you can compact data and how you select the files that form a particular blob. Once the data is compacted, the embedded indices within the blob get updated. The data, the blob name that is on the cloud actually has a very specific format. It contains the client IP where the compaction took place, the offset of the footer so that you can easily locate the footer's location in a blob, and the date so that you can know after a point in time which are the blobs that were updated in cloud. After the blob is pushed to cloud, the blob table gets updated with new extents for a file. This is the global blob table that we're talking about, and it always maintains the updated location of a file. If a file is buffered on the client, this blob table contains the client's IP address. And if the blob has been pushed to cloud, then it contains the blob's object ID and the file's extent in the blob. So how would a read request be served? It depends on whether the data is buffered or it is pushed to cloud. Because the blob table contains the location of the data, if the data is actually buffered on a client node, then we could employ client-to-client transfers for reads. If the data has made it to cloud, then a read request can be sent to the cloud for the blob. The interesting part is that today, cloud providers allow range read requests for cloud objects. That is, you can read a small portion of the object instead of reading the entire object. So if you know the extent of the file within a blob that you can obtain from the blob table, you can actually just issue a read request for that particular range in the cloud object. In fact, you may also want to fetch a little more than what is just needed because that is the essence of prefetching. So if you imagine a system where similar files get packed together and compacted together, then by issuing range reads of appropriate size, you may perform prefetching from cloud and that may give performance benefits. How would you handle deletes and renames became an interesting question for us. So when a client issues a delete, the file must be removed from the blob table so that no future reads or writes can go to the file. But you cannot go and delete the file from a given object in the blob. What we instead do is periodically check the liveness of a blob. A blob will contain many files and some files may get deleted or moved over a period of time. By maintaining the liveness of a blob, we can actually look at multiple blobs that have lesser than a threshold amount of live files and take the live files out of them, repack them into a new blob and update the global blob table. Renames are to be handled in a similar way. Renaming is an atomic update of the file's name in the blob table. And the way we do it is that we piggyback on future blobs embedded indices. So for recovery from embedded indices, the blobs are read in the order of creation. And that is why the name of the blob in the cloud contains the date. So the latest blobs will always contain the rename information. A lot of things can go wrong in such a system. The entire blob table may disappear because the system that was hosting it, that is the master, went down. Or one of these clients that are actually performing the compaction can go down. The way we solve it is we periodically back up the global blob table to cloud. On a crash, the last checkpointed blob table is read, and all the blobs that were written after that point in time are read, and we recreate the world. The clients that go down also mean that the files that were buffered for compaction are lost. These files can still be recovered if they were persisted on the local disk and the same machine is available. However, if compacted and pushed to cloud, the blob table will contain all the information for recovery. If compacted and pushed to cloud, but the blob table is not updated, then the embedded indices contain the information for recovery. This is why having both the global blob table and the embedded indices for fault tolerance give us benefit. And here are the results. When we were creating and writing 24.4 gigabytes worth of 8 kilobyte files to S3, we saw the price reduction by 25,000x and a throughput increase by 60x. Cloud file systems should aggressively compact these small objects. It is similar to how file systems work, where small random writes are not as beneficial as large sequential writes. In case of cloud, we would want to change these small objects into larger blobs. And we see that the reason this is because there are significant costs for operations and rate limiting that is added by cloud. By using this solution, we were able to increase the throughput by 60x and the costs were reduced by 25,000x. An interesting use case is backups. So backups of these small files can actually be archived using this strategy to improve both the backup times and costs. And we talked briefly about what policies can be employed for compaction. We want to compact files that are similar in nature, that will live together, be read together, and be deleted together in an ideal world. So a lot of these policies can compact objects by create time. They can compact different files that belong to a single application. And we could also apply learning to choose which objects to compact together. Objects that have a similar read profile will actually benefit from prefetching the entire blob. Thank you. Please feel free to reach out to me on LinkedIn, email, or Twitter. Here is the relevant information.